صبحكم الله بالخير والعافية. Okay. What was the last lecture we teach here? Okay, what was the last lecture? Two lecture. Okay. Two lecture, this means, let me, lecture one, introduction, okay? Introduction, and yes, introduction to performance evolution, and lecture two, probability overview, okay. Probability overview. We finish lecture two or not? Do we finish lecture two? I think I don't finish this lecture, okay? Exactly, okay. Let me upload this there. Probability overview. Let me upload this lecture. It is uploaded. That is uploading now. Okay. So PC file server, recovery block diagram, okay? In what is the number of number slide? The last slide here. Alaikum salam. Recovery block diagram 47. Okay. Okay, parallel. We say serial system, so we go to parallel system. Okay. Parallel system in reliability block diagram, a system consisting of n independent components in parallel. You can see here R1, R2 until Rn. And it will fail to function only if all n components have failed. But if, for example, at least one of these components can work, the system can continue to work. EI, that is the component I, is functioning, and EP, the parallel system of n component, is functioning properly. So EP bar, the parallel system has failed. That is the parallel system not working. When a parallel system failed, so that all components have failed, that is E1 bar intersection E2 bar intersection En bar. Why? Because EI come back. EI, that is component, is functioning. But when component failed, all components fail, the system will be failed. Therefore, probability of EP bar, that is not working parallel system, that is probability of E1 bar intersection E2 bar intersection En bar. Because the failure of each component is P of E and probability of EP equal 1 minus probability of EP bar. Reliability for parallel system. Product law of unreliabilities, so that reliability of parallel equal 1 minus product I equal 1 to n, 1 minus Ri. Because when the all component fail, the system will be failed. The failure of first, that is 1 minus R1. Failure of second, 1 minus R2, until failure of n, 1 minus R. That is failure here. Failure of parallel system. All failure. 1 minus failure, that is reliability. Or reliability of parallel system with time t, 1 minus product I equal 1 to n, 1 minus RIT, where Ri is the reliability of component I, or exponential distribution. So that RIT equal E exponent minus lambda IT. Then RPT equal 1 minus product I equal 1 to n, 1 minus E exponent minus lambda IT. So availability for parallel system, assuming independent repair. This means repair of each component can independent from repairing of another component. AP equal 1 minus product I equal 1 to n, 1 minus L. And this means the system parallel well available, so that at least one component available. And here, that is component not available, that is product. 1 minus Pi equal 1 to n, mean time to repair of component I, divided by mean time to failure component I plus mean time to repair component I. Because in the repair, the system not available. Or APT equal 1 minus product I equal 1 to n, 1 minus IT, where I is the steady state or transient availability of component I. Homework. For a two-component parallel redundant system with EXP lambda behavior, write down expression for RPT and mean time to failure for parallel system. Further, assuming EXP mu behavior and independent repair, and write down expressions for APT, AP, and downtime. Another homework. For a two-component parallel redundant system with EXP lambda 1 and EXP lambda 2 behavior, write down expression for RPT and MTTFP. Assuming independent repair at rates mu1 and mu2, write down expressions for APT, AP, and downtime. That is the homework. But series parallel system, that is combination of serial and parallel system. We can see in this figure we have two control and three voice channels example. A system is up as long as one control, at least one control and one voice channel are off. But if, for example, two control fail or three voice fail, the system will be failed. But if one of these work, for example, this control and this voice, this serial can, this system work. The whole system can be treated as a series system because control is series voice with two blocks, but each block being a parallel system in this figure. Each control channel has availability RCT, and each voice channel has availability RVT. System is up if at least one control channel at least voice channel are up. So for control channel, probably the failure for the system, that is 1 minus RCT exponent 2, that is failure. This means two control will be failed. And with voice channel, 1 minus RVT exponent 3, that is failure. But in reliability of this, that is 1 minus this for channel and for control channel, for voice channel. So that the product of this, that is the reliability of series. Okay. Homework. Specialize formula 3, previous formula, the case where RCT equal E exponent minus lambda CT and RVT equal E exponent minus lambda VT. Derive expressions for system reliability and system mean time to failure. Based on that. So, yes, we can send this homework not now, in the date of exam. In the date of exam. All homeworks. A workstation's file server example. Computing system consisting of a file server, two workstations, computing network connecting them, and system operational as long as one of the workstation and the file server are operational. And computer network is assumed to be fault-free. Here you can see this workstation file server, WFS workstation file server from computer via computer network connected to two workstation, workstation number 1 and number 2. So, recovery block diagram for workstation file system example. We can see two workstation is parallel, but connected to file server in series. Yes, all slides are important because that is the abstract of the book. RWT, that is workstation reliability, and RFT, that is file server reliability. So system reliability is given by this formula. The failure rate for workstation reliability, that is 1 minus reliability T exponent 2, that is failure. So that the reliability, that is 1 minus failure for workstation, multiply RFT for file server, that is reliability of parallel series system. Note that applies to any time to failure distributions. No problem distributions, maybe for example exponential or Poisson or other. Assume exponentially distributed time to failure. Failure rate and workstation lambda of W, lambda index W, and failure rate of file server lambda F. So with substitution this in the previous equation here, here, and here. So 1 minus 1 minus E exponent minus lambda WT exponent 2. That is reliability of this, that is E exponent minus lambda W. Multiply exponent minus lambda F. That is for reliability of the file server based on this here. And the system mean time to failure is given by mean time to failure, that is integral from 0 to infinity of reliability, RTDT. And if you can integral from this formula here, you can see this 2 exponent lambda W plus lambda minus 1 divided by 2 lambda W plus lambda. For exercises, reach to this, compute this. And solve this integral. So here you can see comparison between exponential and variable distribution. The horizontal axis is time, vertical is reliability. When time increases, reliability decreases. This means the probability of the system fail in the lifetime will be more. But reliability of exponential is better than reliability of variable, you can see. Availability modeling for the WFS example. Assume that components are repairable, so that mu W repair rate of orchestration and mu F, that is repair rate of file server. That is lambda W and lambda F, that is comeback, lambda W and lambda F, that is failure rate, and mu W and mu F, that is repair rate of orchestration and file server, respectively. Availability, AWT, that is availability of orchestration, that is availability of orchestration, mu W divided by lambda W plus mu W, because in repair rate, the system not available, plus lambda W divided by lambda W plus mu W, E exponent minus lambda W plus mu W, T. And AFT available of file server, similar to availability of orchestration with this formula. because in the repair rate system it is not available. So system in instantaneously availability AT is given by this formula. Availability of T equal 1 minus AWT exponent 2 minus AFT. The steady state system availability is the limitation of AT when T go to infinity. That is mu W2 plus 2 lambda W mu W multiply mu F divided by lambda W plus mu W exponent 2 multiply lambda F plus mu F. Homework. For the following system, write down the expression for system availability. You can see here we have a series system, 5 block, but some block is parallel. For example, block 3 and block 4. Assuming for each block a failure rate lambda and independent restoration at rate mu I. K of n system in recovery block reliability block diagram. System consisting of n independent components, and the system is up when K or more components are operational. This means at least K component must be alive and working. Identical K of n systems, each component has the same failure and or repair distribution, like this. And the non-identical K of n system, each component may have different failure or repair distribution, so that in identical K of n system, all components same repair distribution, but in non-identical not the same. No, you must search for solving this in the internet and books. Reliability of identical K out of n system. That is reliability of K of nt. That is failure y n minus K plus 1t. This means when K component work, n minus K plus 1 not work here, failure. That is summation of J equal K to n J from n RTJ 1 minus RT exponent n minus J here. Why? Because, for example, we have, 10 components, okay? If 10 component, for example, K equal 4, so that 10 minus 4 plus 1, that is 7 component. If 7 component or more, for example, 7, at least 4 components must be work. But if 7 or 8 or 9 or 10 components fail, the system will be failed. Here, that is J equal K until n. So that is when 4 RT exponent J 1 minus RT exponent n minus J. That is for reliable. and then 5 reliable here, j equal 5. 6 reliable, j equals 6. If j equals 6, for example, 10 minus 6, 4 not available. And then summation with each other, reliability. Because that is or 4 work, or 5 work, 6 work, until 10 work, all work. But if, for example, 3, if 3 can work, that is not reliability, because that is below the 4. RT, that is 1 minus failure T, is the reliability for each component. K equal N, that is series system, reliability of series system, that is RT exponent N. And K equal N in this formula for parallel system. Parallel system, that is J equal 1 to N. If K equal N, that is N to N. That is RT N, 1 minus RT N minus N, that is 0. But if K equal 1, summation J equal 1 to N, and combination 1 from N, RT J until 1 minus RT N minus J. That is 1 minus RT exponent. That's parallel. Steady state availability for identical K of N system. Identical K of N repairable system, the units operate and are repaired independently. And all units have the same failure time and repair time distributions. And the unit failure rate, that is lambda equal 1 divided by mean time to failure, and unit repair rate, mu equal 1 divided by mean time to repair. So, in identical K of N repairable system, the units operate and are repaired independently. And all units and failure rate is independent and equal for all. All units have the same failure rate and repair time distribution. Unit failure rate, lambda equal 1 divided by mean time to failure. Because here mean time to failure, that is until the system work, that is lambda, working rate. And unit repair time may equal 1 divided by MTTR, because the rate that is inverse of the period and time. A steady state availability for identical K of N system. A steady state availability of identical K of N system, that is A K of N summation J equal K to N, because at least K component should be work. Mu divided by lambda plus mu exponent J multiply lambda divided by lambda plus mu exponent N minus J. That is summation J equal K to N, combination J from N, AJ, multiply 1 minus A, exponent N minus J. Where A equal mu divided by lambda plus mu is the steady state unit availability. Binomial random variable. In fact, the number of units that are up at time t, say yt, is binomially distributed. This is so because t equal x1t plus x2t until xnt, where xi are independent and identically distributed Bernoulli random variables. Another way to say this is we have a sequence of n Bernoulli trials. So White is a binomial with parameters n and p, so that pk, that is probability of yt equal k, that is combination k from n, pk, p exponent k, 1 minus v exponent n minus k. And f of x, big F of x, that is probability of yt less than or equal x, that is summation of k equals 0 to x, combination of k from n pk, multiply 1 minus p exponent n minus k. And the expected value of yt, that is n multiply p. P, that is number of, p, that is probability of success, and 1 minus p, that is probability of failure. And f of x, that is probability yt less than or equal x, because at least x should be work. If less than is work, that is failure. Here you can see binomial random variable PMF. And so, for example, the maximum probability if in 9, excuse me, here in the 8, with n equal 10 and p equals 0.75. You can see here, n equal, and this related to p, n, and k in this formula. P, n, and k. Here that is n and 10 and k. K between, for example, here 0 until 10. And with p, 0.75, 1 minus 2, 0.25. And we can this formula, pk, combination of c and ik. For example, combination of 8 from 10 here. Combination 8 from 10. 8 from 10. Based on here. 8 from 10. P exponent k. That is 0.75. Exponent 8. 1 minus p, that is 1, 0.25. Exponent 2. Because n minus k. 10 minus 8, that is 2. If you calculate this, that is approximately here. But summation of this, that is equal 1. And here binomial, you can see CDF of this, you can see in this figure. Homework. Consider a 2 out of 3 system. Write an expression for its steady state availability, average cumulative downtime, system MTTF and MTTR, and verify your result using Sharp, that is software. The probability of error in the transmission of a bit over a communication channel is p exponent 10 exponent minus 4. What is the probability of more than 3 errors in transmitting a block of 1,000 bits? Consider a binary communication channel transmitting coded words of n bits each. Assume that the probability of successful transmission of a single bit is p, and the probability of an error is q equal 1 minus p. And the code is capable of correcting up to e where e greater than 0 errors. For example, If no coding or parity checking is used, then E equals 0. This means not capable of correcting. But if a single error correcting Hamming code is used, then equal 1. It will assume that the transmission of successive bits is independent. Give the probability of successful word transmission. Assume that the probability of successful transmission of a single bit over a binary communication channel is P. We desire to transmit a 4-bit word over the channel. To increase the probability of successful word transmission, we may use 7-bit Hamming code, 4 data bits, and 3 check bits. Such a code is known to be able to correct single-bit errors. Derive the probabilities of the successful word transmission under the 2 channels, and derive the condition under which of the use of Hamming code will improve the performance. Okay. Do you have any question until here, students? Okay, we have 15-minute break and then continue. Thank you. Assalamu alaikum. Continue to the lecture. Reliability for non-identical K of n system. Here there is not same failure rate and repair rate. Let Cm equal I1, I2 until Im, so that I1 less than I2, less than I2 until less than Im, less than or equal n. N equal 1, 2, 3 until n. The reliability for non-identical K of n system is relativity of K and n, that is summation of Q equal K to n, summation of S belong to CQ, product 1 minus Rj, J belong to n minus S, multiply product of Ri, I equal to S. That is R of Kn, that is 1 minus Rn, multiply Rkn minus 1, plus Rn multiply Rk minus 1 and n minus 1. So that R, that is recursive relation here. here into B. So from the truth table, availability of bridge, that is some of them, A1, A2 plus A1, A2 bar, A3, A4 until the end. That is bridge availability. But here in bridge, the figure of the this circuit depend on the status of tree, component tree. If component tree down, we have here 1 and 2 series, 4 and 5 series, but all parallel. And if C3 is up here, if up, that is connected, so that 1 and 4 is parallel, 2 and 5 is parallel, and all of this series. Here non-series parallel block diagram here. Component tree is chosen to factorial on condition on. Upper resulting block diagram tree is down. Lower resulting block diagram tree is up. Cellular parallelability formulas apply to both resulting block diagrams. Result combined using the theorem of total probability. If A3 down, that is 1 minus A1, A2 multiply 1 minus A4, A5, if down. Come back. If down, here, 1 minus A1, A2, that is failure rate for the top. 1 minus A4, A5, that is failure rate for down, okay? But if that is failure, that is multiplication of this. So that 1 minus A1, A2, and 1 minus A1, A4. Multiplication of this, that is failure rate. And this is failure rate. And availability or reliability, that is 1 minus this. And when A3 is up, A3 is up. Here when up, here failure rate 1 minus A1, 1 minus A4. 1 minus A2 multiply 1 minus A5, failure rate. Here 1 minus A1, 1 minus A4. That is failure, that is failure. But reliability, that is 1 minus this. So that is failure rate. 1 minus reliability, 1 minus failure, 1 multiply 1 minus failure here. So that A of bridge, that is A3 down, multiply 1 minus A3 plus A3 up multiply A3. Why? Because when, come back, because when A3 up, that is 1 here, that is 1 here. But when down, that is 0 here. So when down, when up, that is 1, A3. When down, that is 0. So that 1 minus A2. That is ability of bridge. Homework. Specialize the bridge reliability formula to the case where RIT equal E exponent minus lambda IT. Find the R of bridge T and mean time to failure for the bridge. Specialize the bridge availability formula assuming that failure rate of component I is lambda and restoration rate or repair rate is mu I. Verify your result using SHARP. BTS sector and transmitter example for this. BTS sector or transmitter example, you can see we have 3 radio frequency carrier, that is transceiver plus a power amplifier and the 2 antennas. Need at least 2 functional transmitter passes in order to meet demand is available, and failure of 2 to 1 combiner or duplexer 1 disables pass 1 and pass 2. You can see here we have 3 radio frequency, 1 2 to 1 combiner and 1 demultiplexer, and here pass through, and here that is antenna. We have 3 paths, excuse me. For example, if 1 transceiver and 1 power amplifier can work, that is continue to work here. So measure that is a steady state system unavailability, system downtime, methodology fault repeat events later, reliability black diagram, and factor. We use factoring if any one of 2 to 1 combiner or demultiplexer 1 fail, the system is down, because we have only 1 combiner and 1 duplexer, and that is in serial. If 2 to 1 combiner and duplexer are up, then the system availability is given by the reliability black diagram here. This is with default duplexer 1 and combiner are up. Come back here. Here duplexer 1 and combiner that is on. With this default. So come back. So do you see the picture? Or you don't see the picture? Okay, let me upload, let me enter join. Go to 91. Okay, now I see. Hence, the overall system availability is captured by the recovery block diagram. You can see here. Why here 2 to 1 complexer and loop 1. Come back. Here. Combiner and duplexer. That is 1. That is combiner and duplexer. 2 to 1 and 1. So methods for non-series parallel recovery block diagram. We can use from factoring or conditioning, that is done. Boolean truth table done. We see in previous lecture. And mean passes inclusion or exclusion. And SDP, that is sum of disjoint products, and BDD, binary decision diagram. That is different method you can use here. Homework: solve for the bridge reliability using mean path followed by inclusion or exclusion. But what is the fault trees? Fault trees, combinatorial, non-state space model type, and components are represented as nodes, and components or subsystems in series are connected to OR gates. Components or subsystems in parallel are connected to AND gates. So that series we can OR, parallel we can AND. Component or subsystem in K of N recovery block diagram are connected as N of K plus 1 of N gates. Failure of a component or subsystem causes the corresponding input to the gate become true. But that is fault tree, not reliability tree. And one that is failure. And whenever the output of topmost gate become true, the system is considered failed. Extensions to fault trees include a variety of different gates, sample NOT, XOR, priority AND, spare gate, functional dependency gate, sequencing and forcing gate. Major characteristics: historical complexity, exponential in number of components, and find all minimal cut sets, and then use some of the disjoint products to compute reliability. And then use factoring or the BDD approach can solve fault trees with 100 of components. This is when number of components is large. We can use from minimal cut set, and then use some disjoint products, compute reliability. Here you can see a fault tree example. C1 to C1 bar, C2 bar, that is go to AND, it is parallel, and V1 bar, V2 bar, V3 bar, and the result of this set is OR. OR used from serial and used from and used from series. Come back here, and for parallel and OR for series. OR for series. Here OR for series. Here series and for parallel. Two control and three voice channel example for that. When system failed, when two control 0. Two control 0, that is complement 1. When complement 1 here, that is 1, 1. C1 and C2 fail, that is 1. V1, V2, V3, that is 1, that is failed. Okay, so that here 1. OR and 1 and 1, that is 1 here. But if here, for example, 0, here, for example, V1 0, that is V1 bar 0. V1 work good. here that end of this that is 0, but what of 1 that 1 and 0 that is 1 here. That is cannot work because the controller and the V that is serial. So that the structure function phi equal phi bar C1 bar multiply C2 bar plus V1 bar V2 bar V3 bar. That is phi bar. If phi bar equal 1, that is failure. Failure of the system. Result of the system, assume RCT equal exponent minus lambda CT and RVT exponent minus lambda VT. So that RT, that is 1 minus RCT exponent 2 multiply 1 minus RVT exponent 3 equal to E exponent minus lambda CT minus E exponent minus 2 lambda CT multiply 3 exponent minus lambda 1t lambda VT minus 3 exponent minus 2 lambda VT plus E exponent minus 3 lambda VT. You can see here. File tree for the workstation file system. Example that we see before that. We can see here we have file server, but because workstation 1 and workstation 2 that is parallel, that is here and because file server and workstation serial, that is OR. You can see x1, x2 bar and xf bar. Phi bar equal x1 bar multiply x2 bar plus xf bar. If server, for example, fail, that is 1. That is no problem. For example, here if 0, here for example 1 0, that is 0 and 1, or that is 1. This means fail. This means if server fail or one of the workstation fail, the system will fail. That is reliability expression are the same as the recovery block, the reliability block diagram. Availability modeling using fault tree. Assume that components are repairable. Mu W repair rate of workstation and mu F repair rate of file server. AWT availability of workstation. AWT equal mu W divided by lambda W plus mu W plus lambda W divided by lambda W plus mu W multiply E exponent minus lambda W plus mu W multiplied. AIT availability of file server. AFT equal mu F divided by lambda plus mu F lambda F divided by lambda plus mu F multiply E exponent minus lambda plus mu F multiplied. Availability modeling using fault tree. I will continue of that. System instantaneous availability AT is given by AT equal 1 minus AWT exponent 2 multiply AFT, and the steady state system availability is a steady state equal limitation of AT T go to infinity mu W exponent 2 plus 2 lambda W lambda mu W UF divided by lambda W plus mu W exponent 2 plus lambda plus mu F in the denominator. Summary. Non-status space modeling, non-status space technique like reliability block diagram and fault trees are easy to represent and assuming statistical independence solve for system reliability and system availability and system mean time to failure. Each component has attached to it probability of failure, a failure rate, a distribution of time to failure, and steady state and instantaneous unavailability. Two procedure, three memory fault tree. Two processor, three memory fault tree. Because two processor working parallel, that is here we have and here, but two processor here, for example, we have the same shared memory M3 here, shared between processor 1 and processor 2. But processor 1 has memory 1, processor 2 has memory 2. So that the fault tree example, because each processor has a memory that is parallel, So that there is here and, because that is parallel, and processor with this, that is serial, so that is OR, and also processor that is parallel, that is AND. Specialized for dependability analysis, represent all sequences of individual component failures that causes system failure with tree-like structure. Top event system failure, gates and or not empty of N. Input of a gate, component 1 for failure, if one failure, 0 for operational, and output of another gate, AC component and repeated component. Fault tree, without repeated nodes, we can map a fault tree into recovery block diagram. In recovery block diagram, parallel system in fault tree and serial system in fault tree OR, and n minus k plus 1 of n system, that is k of n gate. Use algorithm for recovery block diagram to compute mean time to failure in fault tree. For fault tree with repeated nodes, factoring algorithm, BDD algorithm, and STB algorithm. Near factoring algorithm for fault tree, you can see M1 and M2 indicated for each processor, but M3 that is the shared. So that if M3 has failed here, that is M3 have failed, that is 1. When that is 1, the AND output of AND be related to M1. If M1 1, the output 1. If M1 0, the output is 0. So that here, that is, can be M1 here, M1 and here M2, like that, if failed. But if M3 has not failed, if not failed, that is 0, okay? When 0, so that the output of AND, that is 0. And the output of OR not dependent to this, that is P1, and that is P2. So that's P1, P2, and that is failure. So that the figure related to the status of memory tree. Okay, this is the last slide of this lecture, and you can see here if you have one processor, and serially go to memory, because that is AND here, memory 1, and processor 2, processor 2, and memory 2 serially. Okay, but that is AND, but here connected to each other from memory 3. Memory 3 that is parallel with memory 1 here. Memory 3 parallel with memory 1 and memory 2 here. So that is parallel, memory 3. And all of this is parallel this processor here. So that is AND, because that is parallel. Okay, do you have any questions, students? In the next lecture, we go to lecture 3, and we don't have class in the Tuesday, and we have another class, additional class in Friday. Yes. So you can contact with me with the email. This is my email. And Insta like that without underline. You can follow me in Instagram. Don't need to now send the homework. You can send the homework at the time. Yes, no class at Tuesday. Yes, Friday. But for the next, we have in Tuesday. Yes. Today we don't have class in the Tuesday. We have the class in the Friday. Like this, like today. Like today. Okay. Do you have any questions, students? Do you have any questions? Okay. Thank you for attention and goodbye.